Hi, I'm Mirren, I'm a final year math student, and today we're going to talk a bit about non-Euclidean geometry, or geometry beyond what we usually think of. So we're going to look at a few topics, including what is geometry, what about Euclidean geometry, breaking the rules, non-Euclidean forms of geometry, visualising hyperbolic space in an unexpected way, and finally we're going to look at where can we go from here. Now, what is geometry? There's actually quite a variety of definitions, but one idea often used to describe it is the science of space. Now, I looked up the definition in the Oxford English Dictionary. The definition that they give is geometry is the branch of mathematics that deals with the measurements and relationships of lines, angles, surfaces, and solids. Now, I'm going to guess that you've probably heard of a certain type of geometry, or maybe you're familiar with it, but you don't know the name. And this is called Euclidean geometry, which is geometry named after a mathematician, a Greek mathematician, from about 300 BC called Euclid. He is actually known as the father of geometry. His ideas around geometry actually dominated this field until around the 19th century, when other ideas about geometry kind of started coming into play. So Euclid actually wrote this book called Euclid's Elements, which actually is a collection of 13 books. And in this book, he describes what he called Euclidean geometry. Often in mathematics, we have rules or axioms that describe the boundaries of the space that we can work in. And Euclid chose to have 5 of these, which are called his postulates. Another word really for rules. And these describe different things about the nature of math. So for example, if you have 2 points, you can join them by a straight line. Straight lines can be extended forever. You can draw a circle, you can have like triangles and all that sort of stuff. And it's all the kind of typical ideas about geometry, because that's the geometry we're talking about. What happens when you have a piece of paper and you draw things, lines and angles and so on it. Euclidean geometry is pretty well behaved. So the angles in the triangle add up to 180 degrees, yep. If you have a line, then you're going to have parallel lines, all the pretty typical stuff. But I'm just going to focus in on that 5th postulate that Euclid has talked about. So this is called the parallel postulate, and actually I'm going to rephrase it in more of a modern way, as the original way is quite confusing. Basically, we've got a line, and then we have a point somewhere else in space. And the question is, how many lines can we draw that go through this point that are parallel to that first line? Yes, the answer is 1. When we think we've got a line, a point, and then we can draw one line through that point. Sometimes when we look at the rules of mathematics, or geometry in this case, they can be a little bit strict, because actually this is not very flexible. We can only work in a 2D space. What happens if we want to describe things that don't fit into this boundary? And so I'm going to suggest that we should break the rules of geometry, specifically this 5th one. So what happens if we chuck out the 5th rule and we just think about the original 4? Other types of geometry arise, otherwise known as non-Euclidean geometry. So today in this video, I'm going to talk about 2 of those non-Euclidean geometries. There are more, which you can go and Google later if you want to, but I'm going to talk about spherical and hyperbolic geometry. Spherical geometry is pretty helpful as our world is spherical, and so we can use it to describe lines and angles and work out where things are in relation to one another and so on. So that's quite helpful. Hyperbolic geometry can be used by physicists in general relativity and special relativity. And when we think about the curvature of space-time, that's where hyperbolic geometry comes in. So what is spherical geometry like? What are the rules like, etc.? So here in front of me, I've got a sphere, which you can see is just an orange. And when we think of lines in spherical geometry, we are actually talking about what are called great circles. So here you can see that this green line is nice and straight, or straightish, but when we rotate our sphere, we can see we've actually got a circle here. Now, that's a little bit weird, but kind of just trust me on that. So now let's talk about parallel lines. We've got a nice green line here, and we've got a nice blue line here, and when we look at them, we can actually see that they look pretty much parallel. But actually, as I rotate this sphere, we see that they cross, that these lines actually cross. And in spherical geometry, instead of the 5th postulate, we add in our own, which basically says there are 0 lines that will go through that point that will be parallel. All lines will converge at some point. Now, what about triangles? I said earlier that in Euclidean space, the angles add up to 180 degrees, which I'm sure you already knew. But when we look at, here we go, we've got a triangle here. We're connecting 3 different points here. And we can see that we've got two angles here which are both pretty much 90 degrees, and then we've got another angle here, but 90 degrees plus 90 degrees is 180 degrees, and that's already the amount that we were allowed to fit into a triangle. And so we can see that in spherical geometry, the angles of a triangle add up to more than 180 degrees. That's a bit weird. But what happens if we think about a space where the angles of a triangle add up to less than 180 degrees? Is that possible? So actually it is, and that is hyperbolic geometry. So again, if we look at this quickly, we can see that this space is curved, and I'm just going to say that this has positive curvature. We can define what is positive and negative in this context, and we define spherical geometry as having positive curvature. Whereas when we think of Euclidean geometry, that's zero. It's pretty much flat. So when we talk about hyperbolic geometry, we're talking about a space that has negative curvature. And I know that for me, well, I can visualize what positive curvature is like, because I can literally hold it in my hand, I can throw it around, whatever, and we can imagine what positive curvature is like. But when we try and understand negative curvature, that can be quite tricky. And you might be asking yourself, well, how can I visualize this? And that's a question that a certain mathematician was asking herself. Now, back in 1997, Taimina was going to a workshop on geometry at Cornell University. And in this workshop, the professor or lecturer, whoever was leading it, was using a paper model to look at hyperbolic geometry. You can see that it's really fragile and actually doesn't do that great a job at visualizing what that space is like. And so she went home and she was actually going to be teaching a course on geometry the next semester. And so I was thinking about, well, how can I visualize this? And she decided that actually crochet could be quite a good way of doing that. And so she made these really beautiful models of hyperbolic geometry using crochet. So I decided I wanted to crochet it myself. And so now you're going to see me crocheting this. As you can possibly see, I was singing along at the time. I was having a lot of fun. But anyway, how do we crochet this hyperbolic shape? So we start off by making a magic circle, which you can easily look up a tutorial if you want to. And then we make a round of 6 stitches. And then you make this crochet in rounds, you kind of go out from the center, and each round you increase every regular number of stitches. So I increased every 3 stitches, but you could increase every 2 stitches or 4 or whatever, as long as it's regular. And so each round, the number of stitches you have will double. Your stitches will be growing at an exponential rate, which is why we get this sort of curviness, as eventually you have more stitches than can fit in a flat space. And that's how we make this hyperbolic shape. So it's actually really, really simple to crochet. And then you won't actually see me do this, but I crocheted some lines through it so we can see and visualize that parallel line thing, the kind of hyperbolic version of Euclid's parallel postulant. So here it is. Here is the hyperbolic surface that I have crocheted. And we can see that it's got quite like a curved nature here, that actually we can't flatten it out and make it fit into Euclidean space, into 2D Euclidean space, as this is the sort of 2D equivalent. But anyway, let's have a look at these lines that we've got here. So we've got our original line and a point here. Earlier we posed the question of how many lines can we draw through a point that are parallel to the original line that we've drawn. And in the Euclidean case it was 1, in the spherical case it was 0, but we'll see in a moment that in hyperbolic case it's actually more than that. So we've got our 1 line here, which we know is parallel. And so when we talk about parallel lines, we're talking about lines that will never converge or meet. So these lines we can obviously see they're not going to meet, that they're nice and parallel. They're kind of, if we extend them on to infinity, they'll look the same. And what about this next line here? Well, actually, if we compare it to this first line, because of the way the space is curved, we know that actually they're never going to meet either. And we can kind of visualize this by almost folding the space. And then we can actually do that again with this line here, because again, it's never going to meet. The gap's almost getting bigger as space moves on. And so in the hyperbolic case, actually infinitely many lines can go through this point that is parallel to the original line. Now that's a bit mind-bending and crazy, but I think it's really cool. And if you want to, you can go away and consider these questions in your own time. What happens in hyperbolic space with quadrilaterals? Do they have 4 angles of 90 degrees? What about circles? What do they look like in hyperbolic space? Maybe go away and crochet one of these if you want to. Now there are many other ways you can explore hyperbolic space. One way that you can do that is through games. A game that you might have heard of is called HyperRogue, and this is a roguelike, which means that it has kind of dungeon-like areas that you explore that are procedurally generated as you go along. And actually the really special thing about this game, which is based in hyperbolic geometry, is you could play and have a fun time. But also there's a sort of tour of the game which allows you to see different models of hyperbolic space to try and understand some of the maths behind it. Now, a few other options if you want to just consider maths that goes beyond your typical experience of maths. Some books I'd really recommend. One is called Things to Make and Do in the Fourth Dimension by Matt Parker. I really like the kind of practical nature of that one. Another one is Alex's Adventures in Numberland by Bellos. And finally, a book that's a bit more related to this topic. Daina, who we were talking about earlier, has actually written a book all about crochet and hyperbolic geometry. Now her book is called Crocheting Adventures with Hyperbolic Planes, and actually it won a prize for the oddest title of the year back in 2009. Another place to look for more content with maths that goes beyond what you expect is Numberphile. They've actually done a couple of videos on Non-Euclidean Geometry, which are really good. Another great video to watch is called The Beautiful Story of Non-Euclidean Geometry by Dr. Trevor Bassett, and that's one I'd really recommend watching. I'll link it in the description below, as well as maybe a few other ideas of things you can look into if you want to explore hyperbolic geometry a bit more, or maths a bit more. Anyway, thank you so much for watching. I hope you've enjoyed exploring geometry beyond what we typically think of. Feel free to let me know in the comments if you've got any thoughts or ideas about what we've talked about today. Maths is really cool. I've loved doing my degree, and I'd really encourage you to keep exploring maths, as you'll find things that you probably weren't expecting. Anyway, that's it from me. See you again.